Alright, welcome to video 5 for, what is this, unit 3? Yeah, unit 3. This is video 5, and this one is going to be about space, and how things like force of gravity and gravitational field strength will change at those extreme lengths and distances. So, like I said, this is going to talk about force of gravity between two objects and gravitational field strength. I'm going to start with the gravitational field strength here. Gravitational field strength is usually represented by little g. We call this little g because in the equation for little g, or in this case, gravitational field strength, there is a value that we represent with the variable big G, or an uppercase G, if you want to think about it that way. In this context, an uppercase G is going to be simply Newton's constant. Newton's constant is about 6.67 times 10 to the negative 11. Usually you don't need to know the specifics for that, though. Also in the formula is going to be m. M is the mass of the planet that we are concerned about. For example, it could be the mass of the Earth, the mass of Mars, whatever. And then, oh, there's a random dot there. And then lastly, in the denominator, we have r squared. R is the distance from this planet's center of mass. So, for example, if I wanted to find the gravitational field strength of, I don't know, like Earth's gravitational field strength when you're 100,000, I don't know, I'm just making up numbers, 100,000 kilometers from the Earth's center of mass, then I would use this formula right here. It would be G, so 6.67 times 10 to the negative 11th, times, I don't know what Earth's mass is, but whatever it is, over 100,000 squared. This one is the pretty simple one to understand. Now we move on to force of gravity. Force of gravity is actually also pretty straightforward. F of g, or F sub g, force of gravity. This one is also going to be a fraction. On the bottom, we still have r squared, and r is still the distance, but in this case, it's between the distance between the two object center of masses. Because this force of gravity, it's the force of gravity between two objects. This is an important distinction to make here. Gravitational field strength is like one object. You're taking that one object and seeing its gravitational field strength r away, or a distance r away. Force of gravity is the force of gravity, or the force of attraction between two different objects. Force of gravity, two objects. Gravitational field strength, one object. Important distinction to make there. Anyway, back to the actual formula for the force of gravity between two objects. Again, we have a g on top. Newton's constant, 6.67 times 10 to the negative 11th. And then that is multiplied by m1, which is the mass of object 1, multiplied by the mass of object 2, or m2. Now, this is actually just a direct application of the more general formula for the force of gravity. We know that in general, the force of gravity, where do I want to write this? I'll write this up here. Force of gravity is equal to mg, where m is the mass of, for example, like the object we're dropping or whatever, and then g is going to be the gravitational field strength. However, in this case, let's see. So I have f of g is equal to little g is just this thing over here. We have the gm over r squared. So now I have gm. In this case, I'm going to make a distinction that this is going to be the planet. Maybe instead of 1, I'll do a p. For mass of planet divided by r squared. And then now I have the mass of object 2. I don't really want to put in O there, so I'll just put 2. And then, as you can see, this is just very similar to our formula for the force of gravity. These are very similar. It's just that I have the little subscripts changed around to adapt to my situation. And you can do that. You can change those subscripts as you need, as long as if you keep that structure of the formula the same. All right, now, for this topic, you can't really do much practice, but I am still going to throw one at you here. Here comes a very bad sketching here. So yeah, bear with me. Let's say I'm going to have a planet here. This is a planet. It has a mass of m sub p. And we have two different objects orbiting it. That's actually not horrible. This one is a distance d away. We'll call this object A, and we'll say that this has a mass. Actually, no, I'll get to that later. And then there's a second object orbiting. I'll put this one down here. This one isn't too bad either. And then this one is orbiting a distance 2d away. We'll call this one object B. So as you can see, object B orbits twice as far away. But let's say object B also has half of the mass. So let's give object B a mass of uppercase M. So then object A, which has twice the mass, this has a mass of 2m. How does the force of gravity on these two objects compare? Let's see. I'm going to write out some answer options here. This might take a while for me to write. One half. Or just plain old this. Alright, I want you to pause this video here and just give this problem a shot. See if you can determine an answer here. Alright, I'm going to assume you have given it a shot now. This is going to involve the formula for the force of gravity, because like I said, we are comparing the force of gravity on the two objects here. So I'm going to start by calculating the force of gravity on object A. The force of gravity on object A is going to be Newton's constant times the mass of the planet times the mass of object A, which in this case is 2m. And this is going to be over d squared. That's a very bad d. FGB is going to be, that's a bad g, Newton's constant times the mass of the planet times its mass, which is just m, over 2d squared. 2d squared is just 2 times d times 2 times d. So that's 2 times 2, that's 4, d times d, d squared. So I can rewrite that as more simply 4d. Now I can start comparing to see like what I need to multiply the force of gravity on A by in order to get force of gravity on B. However, the way I usually like to think about these is I'm going to rewrite these as like divisions. This one I can rewrite as FGB over FGA is equal to 1/8, because I'm just dividing both sides of that by by FGA, right? This one I can do a very similar thing. In fact, it's very similar for all of them. Don't know what I'm saying. This is again going to take me a while to write. Why did I make this so crammed? 1/2, and then FGB is over FGA is equal to 1. This to me, it's easier for me to understand like these little multiplication things that are at play, because sometimes I struggle to think like I'm like, let's see, so this might be 1/5 of the other, but like which direction is it? You know, I like having this division because I'm personally am a mathy person, so it makes sense to me. So now, because I have outlined all of my my answers now as the force of gravity on B over the force of gravity on A, I am going to divide the force of gravity on B by the force of gravity on A. So this is going to be BG times that for D, that divided by, forgot a squared there. Wow, at least I caught that. We are going to run out of space here, aren't we? Give me a sec. I can just shrink that, right? That is not what I wanted to do. Whoops. Into the corner. There we go. And I will take this And I'm gonna move that there. There we go. Now I have more room. Now I want to make that smaller. Close, transform, smaller. Okay, there we go. Now I can live with this. Anyway, this is just going to be g times mass of planet times m over 4d squared multiplied by d squared over that. Because this, like, when you're dividing fractions, that's just the same as multiplying them by the reciprocal, right? In this case, I am just going to multiply this first term by the reciprocal of the denominator, right? Here, now we can start canceling stuff out. The d squareds cancel out, the g's cancel out, massive planets cancel out, the m cancels out. And all that we're left with is just a lot of 1s on the top. So this just becomes a lot of 1s over the top. And then we have this 4 and this 2. 4 times 2 is 8. Boom, we have our answer, 1 over 8. So that means that this option, 1/8 times FGA is equal to FGB. That is the correct option. All right, that will be it for this video. We have one more video for this unit, and the next one will be about circular motion and how we can determine things like acceleration and forces acting on a thing moving in a circle. I'll see you there.